Materials are made up of atoms, which basically means that material stiffness depends on how stiff each of the bonds between the atoms are. Stiffness is basically how much something doesn't want to move, or how much energy it would take for you to change the distance between the atoms, either to move them farther apart or closer together. You can visualize this by plotting energy versus distance between atoms, which we call R. The minimum point on this graph is going to be the equilibrium spacing, or the atomic spacing that is most likely to naturally occur, because it has the lowest energy. If you take the derivative of this graph, you get something called the force separation curve, which basically shows you how much energy it would take to change the spacing between atoms. If you take the slope of this force separation curve at equilibrium, or where force equals 0, then you basically get how quickly the forces that the atoms exert to move back to their original spots will increase as you move the atoms farther apart. And this is Young's modulus, or bond stiffness. But this is just between two atoms. In a real world, materials have tons of atoms altogether. They're a bulk material. And so there's something very similar to Young's modulus called bulk modulus. It is basically Young's modulus, but in 3D. You basically plot energy versus volume. And then you can do the exact same thing. Take the derivative twice, and then normalize by how much material you have. And this gives you bulk modulus. The reason why Young's modulus and bulk modulus are so similar is because volume is proportional to side length cubed. And here, our side length is just r. So when you change volume, you're basically just changing a bunch of r's simultaneously. And that makes the physics the exact same.